Okay, hello, we've got a very quick tutorial here about radians and we'll go on to talk about arc length and sector area. Let's get started. 1 radian, lots of confusion about this. If I was to tell you what a radian looked like, it's an angle, and 1 radian is about that big. That's about 1 radian. If you compare that to something that you're probably more familiar with, if we draw 1 degree, probably that's even too big, 1 degree is about that big. So there we go, 1 degree, 1 radian. A bit like miles and kilometres, a different unit, but it measures angles just the same. How many degrees in a circle? 360. How many radians in a circle? Well, a radian comes about by taking 1 radius, and 1 radius marks out, if we go around the circumference, 1 radian. And so because we know that a radian, if you're familiar with, a radius, if you're familiar with your circle formulas, 2 pi times the radius goes into the circumference, so 2 pi radians go into the full circle. This, I think, is where it gets a bit strange for some people, because they tend to think that that's a formula. It's not, it's a number. 2 pi is about 6.28, and so all we're saying is about 6.28 radians make the full circle. It seems like a strange number to use for a full circle. 360 sounds tidier, but actually, as we'll see, in lots of formulas and lots of mathematical problems, it works much better for us. So, our equivalents, what we can say, 2 pi, about 6.28, is the equivalent of 360 if we make the switch. Sometimes a little c is used. Perhaps the easiest way to think about the switch is if you think of 3.14, about 3 radians, 3.14 matches, is equivalent to about 180 degrees. So if I talk about pi by 2 radians, I'm talking about 180 degrees divided by 2. I'm talking about an angle which is 90 degrees. If I talked about something like pi by 6 radians, I would be talking about something equivalent to 180 divided by 6, about 30 degrees. If I wanted to talk about 45 degrees, well, I'd be thinking about 180 split into 4. I'd be talking about pi by 4 radians. So we can equivalence. We have equivalence between radians and degrees, just a different measure, nothing more. We can still talk about 1 radian if we want. We can still talk about 1.5 radians. We don't have to have pi in there. Pi is just a commonly occurring one because it fits into the full circle. So 3.14 radians, 180 degrees. If you want to make a switch between the two, then what you can do, exactly, you could go from radians to degrees, multiply by 180, divide by pi, and if you wanted to go back from degrees to radians, you shouldn't really need to, but if you wanted, you could multiply by pi and divide by 180. But pi, equivalent to 180, should be able to make the switch and the swap for you. Okay, 2 formulas. Very quickly, what we can see with radian formulas. Let's give me 2 circles. And the idea that 1 radian marks out 1 radius can be very useful indeed. It means that we have a very simple formula that if we have 1 radian, let's say radius of 5, 1 radian would mark out an arc length here of 1 radius, 5. If we went on another radian, we'd mark out another 5. And that very quickly tells us that the length of the arc marked out is the radius times the angle. If we mark out, let's say, 4 radians, and the radius is 3. Then the arc length around the edge here, the arc length is simply r theta radius times angle 12. If we are working with, let's say, pi, and again it is pi that tends to cause the problems with these. People get a little bit hooked up on the idea of pi. Let's put an angle, and let's put an angle of that, which is maybe about 2 pi over 3. And if you're thinking, what's 2 pi over 3? Well, pi 180, pi over 360. Two of those about 120 degrees if you want to make a comparison. So 2 pi over 3 radians, let's call the radius 5. What is the length of this arc here? And the length of that arc there would be radius times angle in radians. Don't try and do this in degrees, it never works. And that will be 10 times pi over 3, which is about 11 or something like that if we put it in decimals, but I'm going to leave it like that. Very good. We could easily work out the flip side of that if we wanted. If we wanted the arc length around the other side, it's the radius times the angle, and the radius is 5, and the angle, well, the angle 2 pi in the full circle, which means that we've got 4 pi over 3, and that would be 20 pi over 3, would be my flip side. And there we go. We've got ourselves a nice, simple arc length formula. Our next formula, what we do here, let's take another couple of circles, is we look at these and we say, what about the area? What about the sector area for these? So let me give you there's 1 radian, and what I want to know is what is the area. And we give you a radius of 5, the area of that sector is given by the formula a half r squared theta. A radian formula, once again, nothing to do with degrees. Put degrees in that, it's wrong. So what have we got? We've got a half the radius squared times by the angle, and bingo, we have got 25 over 2, 12.5 centimeters or whatever it is squared, and we've got it. Okay, let's do one more to finish off. We have a sector, and I'll tell you, I won't give pi in this, I'll tell you that that's 2 radians, I'll tell you that that is 4 radius. Sector area, in fact, let me just go back one step. There we go, sector area, half, radius squared, angle a half. Radius is 4, angle is 2. 16, 8, 16, there we go, 16 centimeters squared. What if we wanted the area of this other sector? Well, easily enough. Sector area, once again, same formula. Radius still 4, but what is the angle? Well, if this angle is 2 on one side, the full circle minus 2 will be the other. The full circle is 6.28 minus the 2 we don't want. Half of 4 squared, 2 pi minus 2. Put it in your calculator if you want, but there we go. Centimeters squared, we have got our area. So there we go. We have 2 very simple formulas. One, arc length, which is the radius times the angle in radians, and secondly we have sector area, which is a half radius squared times the angle in radians, never in degrees, and we have the equivalence that pi radians is equivalent to 180 degrees. And that is our conclusion for radians and simple radian formulae.